video, we will be addressing how to do Lewis dot structures for simple compounds that abide by the octet rule. So let's talk about a few examples. Let's begin with CCl4. How would you do the Lewis dot structure for CCl4? Okay. First thing is you want to count your number of valence electrons. So remember guys, this is kind of almost like how much money do you have in a bank, right? So the number of valence electrons is going to look something like this. We have one carbon, right? So one carbon, how many valence electrons is each carbon? According to the periodic table, carbon is in group 4A, so it'll have 4 valence electrons, okay? So 1 times 4. Plus, what else we have here? 4 chlorines. So 4 chlorines, how many valence electrons does each chlorine have? So chlorine is in group 7A, so we'll have 7 valence electrons. So 4 times 7, 28, plus 4, that's 32 electrons. Now, what we mean when we have these 32 valence electrons, it's like we have $32 in the bank, and we've got to share these 32 electrons between these 5 atoms so that everybody is happy and can satisfy the octet rule. So, we will select carbon as your central atom here. Guys, the rules for selecting the central atom is the one that is the least electronegative. Okay? Or if you have 1 of these and 4 of these, then chances are the carbon is going to be your central atom. Now, the first step is, once you find what your central atom is you've got to make your connections. How many connections must we make here? We need 4 of them to hook up these 4 electrons. So I like to do this right away like that, okay? So chlorine, 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 and chlorine. I've made 4 connections to connect my 4 chlorines to my central carbon. Remember, each line here means 2 electrons. So how many electrons did you do here? Did you use to make your connections? 2, 4, 6, 8. Go back to your bank here. Take away those 8 electrons or that $8. Now, how much do you have left here? 24 electrons, correct? Here's what you do next. You say to yourself, I must fill out the outside electrons first. So chlorine is here. I must fill those out to satisfy my octet. Here, chlorine has 2. So how many more does it need? It needs 6 to make the 8. So we're going to do 1, 2, 3, 4, 5, 6. Okay? Now, same thing with this chlorine and this chlorine and this chlorine. So let's count. That's 6 here, 6 here, 6 here, 6 here, and 6 here. So 6 times 4, that's 24 electrons used. We got none left, and that's good, okay? So you want to lastly check yourself. Is everybody happy here? And when I say happy, I mean, does everybody have a full octet, right? So the chlorine does, that's 8, that's 8, that's 8, and that's 8. Carbon, it's got 1, 2, 3, 4 bonds. 4 times 2 is 8 electrons. So everybody is happy like that, okay? And so this would be a sound Lewis structure for that. Let's do another example. Let us look at pH3, okay? So we're going to do the same process over again. pH3. We're going to count how much money we have. We have 1 phosphorus. And if you look on the periodic table, phosphorus is in group 5A, so it has 5 valence electrons, plus 3 hydrogens, and each hydrogen is got 1 valence electron because hydrogen is in group 1A. So 3 times 1, so we have 8 total electrons that we have to share here. P is phosphorus, is your central atom. That's the first step. Then we've got to make connections. How many connections must we make here? It has to be 3, right? because we have 3 other atoms that we need to hook this up to. So I'm going to make 1, 2, 3 connections. How many electrons did I use from my bank to make those connections? 6. So I'm going to take that away. How much do I have left? 2. Now, typically what you would do is fill out the outer electrons first, right? Or the outer elements first to satisfy the octet. But what do we know about hydrogen, guys? Can hydrogen ever have more than 2 electrons in its shell? No way, right? Because hydrogen is found in the first shell, and it literally has no space in its orbitals to fill. It's only got the 1s orbital, can fit only 2 electrons. So hydrogen in helium would abide by what we call the duet rule, right? Meaning that it can't fit any more than 2. So low maintenance, right? Hydrogen is all good. It doesn't need anything else in there. It's good with 1 bond. Now, what do we do with these 2 electrons that are left over? We stick them on the central atom. So, how much do I have left? Nothing. Okay? So, here you can see that everybody's happy because phosphorus has got 2, 4, 6, 8. Hydrogen is, each of these hydrogens has got 2, so that makes everybody good here. Let's do another example. Let's do H2O here. So I'm going to do H2O, which is water, right? And I'm going to do the same thing. I'm going to count how much money do I have. I have 2 hydrogens, correct? Each hydrogen is 1 valence electron, so times 2 plus. I have 1 oxygen, and each oxygen has 6 valence electrons, so I have 8 electrons that I have to share between these 3 lovely atoms, so everybody has a full octet or a duet, and they are energetically happy, right? Or stable. So, central atom is the oxygen, because there's 1 of that and 2 of those, so chances are it's going to be in the middle. But it's because oxygen is the, in this case, is going to go in the middle because it's an exception. Usually you have the one that's more, least electronegative go in the middle, but that can't happen for water because it's not like you can have a hydrogen in the middle, right? If you put H, oh, what's wrong with that? We just broke the laws of physics right here, right? Because H cannot have more than 2 bonds, so there's no way that can happen either, right? So we're stuck doing it this way. That's why in this case oxygen goes in the middle. All right, now let's see what we got. We made 2 connections. That's 4 electrons. Let's take that away from the bank. We got 4 left over. But of course, we know these 2 H's are already good. They already have their 1 bond. They don't need anything else. So what must we do with those 4 electrons? We'll put them on the central atom like this. Okay? And so that would be the Lewis-Dot structure for water. All right, let's do another example. Let's do, I have H2CO. Okay, so we have 2 hydrogens at 1 valence electron each, plus 1 carbon at 4 valence electrons each, plus 1 oxygen at 6 valence electrons each. So that's 12 total electrons that we have to share between these 4 lovely atoms. Now I'll tell you, carbon is going to be the central atom here because it's the least electronegative. And so you're going to ask yourself that we're going to make how many connections? We got 2 hydrogens and 1 oxygen, right? So I'm going to put the oxygen here, and I'm going to connect the 2 hydrogens here, okay? So how many electrons did I use to make these connections? 2, 4, 6. I'm going to take that away from my bank here, right? And I have 6 electrons left. Now, I don't need to put any more dots on the H's because they already have their 1 bond, they're good. So I will start to put 1, 2, 3, 4, 5, 6. Okay? And then I'm gonna subtract that. I got nothing left. Now, the question that you want to ask yourself is, Is everybody happy here? Does everybody have their full octet or duet? And you say, well, oxygen does. This has got its duet, so it's good. But what's wrong with carbon here, guys? It's only got 2, 4, 6 electrons on it, which makes it very unhappy, right? It wants its 8. So, some of you will be very tempted to put 2 dots on that. But what's wrong with that? Let's count our electrons now. 2, 4, 6, 8, 10, 12, 14. Look at this. You only started out with $12, not $14. So you put yourself $2 in debt like that, 2 electrons in debt. That's not going to happen. In the world of electrons, there are no credit cards, right? If you don't have the cash, you can't spend the money, right? So that is not right to do that. So, oh my goodness, what else do we do now? How can we make everybody happy? Well, communism will tell you what, right? When there's not enough to go around, you have to do more sharing, right? So, we're going to have to take these electrons, 2 from oxygen, and we're going to bring them in here to make a double bond. So when that happens, this is how this looks like. Now I got that, and I have this on here. Now, let's double check them, because see, when I use these, I erase them from the oxygen. They're no longer on the oxygen. Now they're being shared between the oxygen and the carbon. So let's see what we got now. 2, 4, 6, 8, 10, 12. Good. So we didn't go past our budget of $12 or 12 electrons, right? And at the same time, look, carbon now is happy. 2, 4, 6, 8 around it. So is oxygen, right? Because look, oxygen here still 2, 4, 6, 8. Carbon still has 2, 4, 6, 8. Notice that the bonded electrons are double counted because that's what they are. They're being shared between the carbon and the oxygen bond. Okay? So that's how you address this idea of how you make double bonds. All right, let's do another example. Let us, this red marker is hard to erase. All right. So let's talk about SO2, okay? Sulfur dioxide. How do you go from there? Okay, so same idea, count your money. Sulfur is in group 6A, and there's 1 sulfur and 6 valence electrons each, plus 2 oxygen at 6 valence electrons each, so that gives you 18 total electrons to share. Sulfur is gonna be the central atom here, and we're gonna connect 2 oxygens to it, okay? To make those connections, we used up $4 from our bank, right? So, for 4 electrons, we got 14 left over. The rules say fill out outside elements first. So oxygen needs, it's already got 2, it needs 6 more. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I just used 12. I have 2 left over. Where do those go? On the central atom. Okay. Now, you still got to ask yourself, is everybody happy? So let's erase that here now that we got that. So we got nothing left. And just double check. 2, 4, 6, 8, 10, 12, 14, 16, 18. That's what we started. It's a good idea to always, like after you draw your Lewis structure, just count your electrons. Make sure that what you have in your Lewis structure is what you started with over there. But what's the problem here? Sulfur is not happy, right? He's got 1, 2, 3 pairs, which is 6 electrons, and we're trying to get the octet rule. We need 8. So when we don't have enough to go around between everybody, we don't just magically create electrons, do we? We don't do that. We do more sharing. So it doesn't matter which one of these oxygens that you work with, but let's do this one. And you bring in these electrons and you share them, and look at what happens. This becomes a double bond here, correct? And this becomes single, and you still keep those on here. So this is the correct way of writing this, okay? Now, everybody's happy. Sulfur's got its 8, and now we have 2, 4, 6, 8, 10, 12, 14, 16, 18. We're good to go, right? And we've learned how to use double bonds regarding this particular Lewis dot structure as well. All right, let's do, oh, by the way, guys, if some of you put this on your paper, it would be the same thing. These are what we call resonance structures of each other, but that's for another topic and for another video. I'm not going to get into that now. But these would be marked just fine either or. Okay, it doesn't matter which one of these oxygen, the sulfur oxygen double bond. It doesn't matter which side it goes on. All right. Let's do another one. I'm going to use my red marker. This is drying up, so we're gonna do CO2 now. Okay, CO2. Still, same thing. We've got to count your money. We have 1 carbon at 4 valence electrons each, plus 2 oxygens and 6 valence electrons each. 12 plus 4 is 16. Cool? Now, carbon is gonna go in the middle. You're gonna make 2 connections here to hook up your oxygens, okay? 2, 4, you've used up 4 electrons. Now you've got 12 electrons, okay? Fill in outside first. So, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Hey, that's 12. We got nothing left, but we have problems. The problem is that the oxygens are happy, but carbon is not. So, in that case, we've got to do more sharing. And that involves, here's this lone pair coming in here to make a double bond, okay? So once I did that, guys, I'm gonna erase it from here, okay? Is carbon happy now? Nope. So we've got to do more sharing. And I'm gonna come around from this side, and I'm gonna do this. Okay? And now I'm going to erase it because now it's being shared. It's not a lone pair anymore, right? So you end up now with this Lewis structure. So let's count to make sure everything is okay. 2, 4, 6, 8, 10, 12, 14, 16. That's what we started with, so awesome, okay? But we want to make sure also everybody's happy. Carbon has got its 8, right? Oxygen's got its 8, and this other oxygen's got its 8. So, let me ask you something. Maybe some of you are thinking, why didn't you do it like this? A triple bond like that and a single bond like this. Would that be right? Okay, so this would be like what we would call a resonance structure of it. But I want to remind you guys that this is more sound without getting into a formal charge per se, but I'll tell you something. Oxygen is in group 6A, right? So oxygen has got 6 valence electrons, correct? So how many bonds does oxygen like to form to get its full octet? Remember, it needs 2 more bonds. So that's why here oxygen is doing a triple bond. You don't find that too much in nature, right? So you know that. Use the things that you learned previously. Oxygen typically likes to form 2 bonds, so double bond. Carbon likes to make 4 bonds, and so you see the 4 bonds around it. Use that as your guide, okay? So that's why it's not this, okay? But of course, you can be more sure and you can do formal charge, but again, that's for another video on another day. All right, let's see what else we got here. Let's do HCl. HCl, same deal. Let's add everything up. See how much money we got to share between these 3 lovely electrons. 1 hydrogen at 1 valence electron each, plus 1 carbon at 4 valence electrons each, plus 1 nitrogen at 5 valence electrons each. 5 and 4 and 1 is 10 electrons, right? Okay, so carbon is going to be the central atom because it's the least electronegative. So we're going to go here and make our connections like so. Okay. Let me try to erase this. Okay. So, to make those two connections, I use the 4 of my electrons, and I have 6 left. Now, hydrogen is good because I don't need to put anything around hydrogen. It's already got its one bond. I fill in the nitrogen, and that's got 2, and it needs 6 more. So that's that, right? We use this up. Now we have 0 left. Here's a problem. Not everybody's happy. So when we don't have enough to go around, what do we have to do? Share, okay? So we're gonna do 1 share, and we're gonna bring it in to make a double bond, okay? So we'll erase that now that it's shared electron. Is this good? Nope, because this is 2, 4, 6. We need 1 more. Remember, carbon likes to form its 4 bonds. So we're just going to take another electron pair, bring it in to do that triple bond. Now you saw that I didn't touch this at all because this had nothing else on it, right? It's already, it has 1 single bond, so it's good. So this becomes the Lewis dot structure for HCN. Now, double check yourself. What do you know about nitrogen? Nitrogen is in group 5A, yes? So it likes to form 3 bonds to satisfy the octet rule. So look at that, nitrogen has got 3 bonds, okay? Use that as, now that doesn't work every single time, but it's a general idea to help you figure out if you're going in the right track, okay? Now, the next question that I want to ask you, how do you do Lewis structures for like charged ions? Right? So for charged compounds, how do you do the Lewis structure for that? And the first example that I want to pose to you is NO3 negative, which is the nitrate ion. Okay? So let's see how that works. NO3 negative. All right. We have 1 nitrogen at 5 valence electrons. We have 3 oxygens at 6 valence electrons. And since this is a negative, guys, what does that mean? You've gained an electron, right? Because electrons are negatively charged, so if you gain electrons, you become more negative. So, and how many did we gain here? 1. So you've got to add it when you are dealing with an anion. Negatively charged, just add however many electrons to your sum right here. So this becomes 18 plus 6 is 24 total electrons. Nitrogen is your central atom. We need to make 3 connections to put my oxygen on there. So we used up 6 electrons. That gives us 18 electrons left. All right, what do we do with these 18 electrons? We fill outside first. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 3, 18. So we use that, we got 0. All right, problem. Nitrogen is not happy because it's got only 6 electrons around it. So just grab any of these electrons on any of these oxygens. It doesn't matter. Just pick one, right? And so we're going to do here, and we're going to bring this in to make a double bond. And once we brought it in to share, we got to get rid of it on the oxygen, right? Let me fix that so it's nice here. Okay? So let's count and make sure everybody's okay. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's what we started with, so we are good. That is my Lewis structure for nitrogen. But when you guys are dealing with anions or cations, put brackets on this and put the charge out here. Don't forget that part, okay? Now, what about if you have like something that's positively charged? What are you going to do, guys? So you're going to take inventory or some of the amount of electrons that you got, right? But since it's a cation and it's positively charged, it means you lost electron, 1 or more electrons. So let's let's do an example of that. When you lose an electron, you have to subtract it from your total, right? So let's see what we got here. All right, we have NH4 plus, okay? Here's the deal. Same idea. One nitrogen, 5 valence electrons each, plus 4 hydrogens at 1 valence electron each. Now, since this is plus 1, means we lost an electron. So what do you have to do? Because when you lose an electron, you become more positive, right? So if you lose negativity, you become more positive yourself. So you've got to take this away. So 9 minus 1 is 8 valence electrons. Cool? Nitrogen goes in the middle. We need to make 4 connections. There's that. And so we used up 8 electrons. That's 0 left. Is everybody happy? Absolutely. Nitrogen has got its 8 and hydrogen has got its 1 bond. But don't forget, because this is a cation, right? We're going to put brackets on this, and we're going to put a plus, okay, to remind us of that. All right? So that sums it up for doing simple Lewis dot structures for up to tetrahedral compounds that abide by the octet rule.